Today we're going to be talking about the states of matter and the kinetic molecular theory. This is a new unit after our little mini unit on stoichiometry. This unit's going to take us a couple of weeks to get through. There's lots of good stuff in here. Hopefully you'll find it somewhat interesting. So the first thing we're going to talk about is what is pressure when we're talking specifically about a gas. And pressure is the force created by the collision of particles with the walls of their container. So if we envision that molecules are in some type of a box and they're moving around, pressure is caused by them colliding with the walls of their container. And we can kind of see this if I go into this little simulation here. If we put some gas molecules in here and they start moving around, as they bump into the walls of their container, that's what generates air pressure. That's kind of what we're going for there. Let's go back to the presentation. As you decrease the volume of the container, if you make the container smaller, the particles are going to collide with the walls more frequently and cause the pressure to probably go up. And then if you increase the temperature, the particles are going to start moving faster, and they're going to hit the walls of the container more often, and they're going to hit the walls of the container harder, which is probably going to make the pressure go up. So these are some of the little basic concepts we're going to be working with. Now, pressure of gases can be measured in several different units, including kilopascals, atmospheres, millimeters of mercury, and torr. And torr is named for the Italian scientist Torricelli, who developed the first barometer that's used to measure air pressure. And a torr and a millimeter mercury are the same thing. Now, just to kind of show you a relationship between these things, 1 atmosphere of pressure is 101.3 kilopascals, or 760 millimeters of mercury, or torr. Or to put that into something you might be a little more familiar with, it's 14.7 pounds per square inch, or PSI. So that's kind of what all these pressure numbers have to do with each other. We're just going to do one more slide on the kinetic molecular theory of gases, and then for the rest of the day, I've got a simulation for you to play with and some questions to answer about that. So the other thing we're going to talk about today is the kinetic molecular theory of gases. This is kind of the framework that we work with when we're trying to understand how gases behave and why, because keep in mind a theory is an explanation. So we're going to try to explain some observations about how gases behave using this. And it's got 5 assumptions, or 5 things that we basically assume to be true in order to help us with our explanations. The first thing is that gas particles are made up of tiny little particles that are constantly moving. They never stop. The second part of this is that the volume of the particles is very small compared to the distance between them. Right? So it's not like, for instance, in a ball pit, and if you've ever jumped in one of those ball pits with all the plastic balls where they're really big balls and they're really close together. For gases, it's the opposite. We assume gas particles are really, really small, and compared to the size of the particles, they're very far apart. The third thing is that collisions between particles are completely elastic. In other words, if they hit each other, they bounce off and just keep going. It's kind of similar to imagining them all as being those little rubber super balls or bouncy balls that you can throw and they just keep bouncing all over the place. Unlike, for instance, a car crash, which is not elastic. When 2 cars collide, they don't just bounce off of each other and keep going the opposite direction. The cars crush up and absorb all of that energy. Gas molecules don't do that. They just bounce off of each other if they hit each other, and just keep on going. The fourth thing we assume is that there are no forces of attraction or repulsion between the particles. They don't stick together. They don't hide from each other. It's kind of the opposite of students in the hallway on a normal day at Topsail High School. We've got some people that are like making out in the hallways and sticking together, and other people are like, ew, I don't want to talk to that person. Let me go down this stairwell over here. So it's kind of the opposite of that. Gas molecules basically just ignore each other and just keep on going about their day. The last thing is that the average kinetic energy of the particles depends only on their temperature. In other words, the hotter it gets, the more energy they have and the faster they go. The colder it gets, the less energy they have, the slower they move. And in fact, this will take us to a very key point. If you get it cold enough, the molecules will stop moving altogether, and we call that temperature absolute zero. And any gas that follows these assumptions is what we will call an ideal gas. And that's all the notes we're going to go through today. The other thing I want to do is show you how to get through this simulation. So when you launch the simulation, you're going to have 4 different options. We're going to be focusing on the one that says ideal. And this gives you a bunch of controls. You can pump some gas molecules in here. You can increase or decrease the temperature. You can change the volume of the container. And you can even open the lid and let some molecules escape. You can also decide that you're going to hold the volume, the temperature, or the pressure constant. And when you hold the pressure constant, you can either hold the pressure constant by allowing the volume to change, or you can hold the pressure constant by allowing the temperature to change. And I'll let y'all kind of play with some of this stuff. I don't want to give too much away. The other thing you can do is you can switch between big particles or heavy particles and lightweight particles. Let's imagine that one is a really heavy gas molecule based off its molar mass, and the other one is a lighter weight one. And they're represented by either being larger or smaller. So that's what I've got for you today.